we'll kick off now. We've got an hour session now until 3:15, in which we're going to talk about Mbed, Mbed 2.0, in the context of Hello World. Okay, so the schedule for this next hour is going to be a few slides to talk about Mbed, why it came to exist, the research that we did beforehand, and really where the platform has got to now and where we see it going to in the future. And I'd like to take some time to do some sort of hands-on labs sessions from the front, just to show you some of the sort of capabilities that the Mbed platform has, and hopefully how easy it is to get going and get started with Mbed-based designs. Okay, so the first thing is the introduction to the Mbed microcontroller. But first of all, we'll just take a few moments to think about what's happening in the world of microcontrollers, and this slide really captures what really inspired the Mbed project to start with. So, three observations that we made back in 2005 have really led us to where we are now. And the first one is that microcontrollers are getting really cheap nowadays. It sounds like a very obvious thing to say, but back in 2005, 2006, an ARM-based CPU inside a microcontroller was actually still quite expensive, of the order of $10. And for many design wins that uses microcontrollers, it really was far too expensive and far too high-end for sort of mass adoption. But here we are sort of 7 years later, where a Cortex M0 Plus MCU can be as little as 50 cents or lower, depending on the volumes that you're designing with. So the message here really is that the cost of microcontrollers has come down by an order of magnitude, if not two, over the last 10 years or so. And this means that all the applications that use microcontrollers in very low-end, low-volume, low-power applications really can start making use of this. The second point is about the power of microcontrollers. So you don't have to go too far back to remember the days when a 10 megahertz MCU was actually really quite high end. Memories were low, capability was low, the sort of interfaces you'd expect were very, very low level as well. But again, if you wind the clock forward to the present day, you know, it's easy to find 200 megahertz microcontrollers, you know, lots of processing capability, you know, hundreds of kilobytes of flash and RAM. So, you know, the performance point that microcontrollers are at now really is quite staggering compared to what it was just 10 years ago. And of course, it's all in a single package, so you really have lots of processing power and sort of capability at your fingertips. The third point is about the interactivity of microcontrollers and the fact that they actually deal with applications in the real world. So generally, a microcontroller is sensing its environment or having some kind of interactive input and output. So if you look at modern microcontrollers that have things like USB host and device on them, or Ethernet, for instance, this really puts a microcontroller into the realms where these things can interact with things that people know and understand from everyday life. And as a conclusion, we think that actually microcontrollers are really pushing forward the boundaries of new product designs and really begin to define innovation in that space. And as such, there's a massive opportunity for microcontrollers going forward. So a long time ago, we had to think about the current state of the microcontroller world and how that maps onto previous things in history. So if you think about what computers were like in the 1980s, well, the only people who really worked with them were academics or people who were sort of professionals in that space. You know, the present day, you know, everyone has laptop computers or tablets or, you know, high power computing at their fingertips. It's just an everyday fact of life. And if we draw some analogies to the world of microcontrollers, currently the microcontroller world really is dominated by professionals, embedded software engineers, embedded hardware engineers, doing sort of product development from a very sort of professional-centric view. And as the technology democratizes, we feel that actually microcontroller technology is going to be picked up and used by people applying it for their own applications, as they do with modern computing. But because microcontrollers interact with the real world, the opportunity and sort of scope for them is far bigger than ever it was for desktop PCs. I mean, most of us in this room probably own a couple of laptops, a desktop machine at work, one at home. So you really saturate at sort of 4 or 5 machines. But you can quite easily understand how you might have 1,000 microcontrollers in your house or many hundreds in your car. Yeah, so in terms of the actual volume opportunity, it's far bigger for microcontrollers and very easy to underestimate. So against that backdrop, you know, what are the barriers for microcontroller adoption? So conceptually, very simple things can be very hard to actually prototype. And as microcontrollers begin to be applied by product designers rather than professional engineers. These are the people that are very creative. They understand what the world wants in terms of products. They might come up with the idea of an SMS cap flap. It's very easy. Anyone could have invented that. But at the current day, it's actually quite difficult to go and build that. And if you go to an embedded engineer and say, well, I want this product, I want a cap flap that can send SMSs, you'd probably get a pessimistic quote of 3 months worth of development. And that's the sort of timescales that sort of creative industries really aren't used to dealing with. And other barriers include things like repetition of choice. So if I want to go and prototype something or have some experiments with microcontroller technology, there's tons of stuff out there. And sometimes that level of choice can be paralysing. So what we've tried to do in the embed world is try and provide people with defaults, try and take away some of that choice for them. So it's not difficult, but it can be overwhelming. And lastly, the overhead of getting started for a new project. So if you're trying to develop a new product, or you've got an idea that you want to experiment with, and your first port of call is downloading a toolchain, configuring your libraries, the amount of time that you actually spend setting up your environment to develop with is probably far longer than you're actually going to spend sort of prototyping. And we think that sometimes the overhead for starting a project is fine if you're going to be on a 3-month development cycle, but if you just want to have a quick experiment with a new technology or a new idea, it can be a real barrier. So against those barriers, we thought about what things were happening in other industries. So if we think about the idea of rapid prototyping, well, it wasn't too long ago where if you wanted a plastic case moulded, you would have to go and talk to a tool maker and have some injection moulds made. And you're in tens of thousands of dollars here and 6 to 8 week lead times. But nowadays, the average product designer probably has a 3D printer on their desk. So now the timescales is hours. You can CAD-CAM a prototype up in the morning and have it on your desk in a very sort of high quality sort of prototype by the afternoon. So timescales have gone from months to hours. And that's also true for things like web frameworks and 2D design. Most laptops are shipped these days with pretty reasonable graphics packages. So if I had a business idea and I was trying to put together collateral, then I can quite imagine sort of prototyping what my packaging is going to be, or my promotional material. And if I was building a new web application, I wouldn't start writing HTML in Notepad anymore. I'd get one of these web frameworks that have been tremendously successful. So all these other industries have their own versions of rapid prototyping. We realised this is what we wanted to do. So if you have a product that includes a plastic case and some 3D design and a web application on the back end, all of that you can do in days. And the electronics side of things really hadn't kept pace, which is why we come up with the idea of Embed, and that's where the idea came from. And we really wanted to position it as a rapid prototyping platform for MCUs. So we really want it to be the fastest way to get started with ARM microcontrollers, and we aim to do that by stripping away all the barriers that you usually have to deal with just to get started. So very simple things like plug and play hardware, and we've provided an online compiler to save you having to set up an environment. And the idea is all the barriers to MCU technology have gone. You can actually get your hands on what you want to build and experimenting with your ideas pretty quickly. Our focus is very squarely on prototyping for a very diverse audience. So this might be hardened engineers, or this might be product designers, or people from completely outside our industry who just understand that electronics can do something for them and they want to experiment. So we've taken a platform approach and trying to build a big developer ecosystem, so there's lots of resources available for people experimenting. Now, even though that was several years ago now, I still bring up the example of the Embed launch that we did at ESC Boston back in 2009. And the reason it's still valid to this day is we made this, does anyone remember Billy Bass, the talking fish? Really annoying toy in the, yeah, okay. So it yammers on at you as you walk past it. So we did an internet connected version of that. We ripped out its guts, we put an embed in there, we gave it a web connection and a Twitter feed. And when everyone sort of tweeted a specific hashtag, it would actually speak the tweet out. It would do a sort of text to speech translation. So it's a pretty dumb application, but the point was we prototyped it in half a day. Now, traditionally, if you'd gone and said to someone, build me this talking fish, that's another 3-month development cycle. And you probably wouldn't bother if it did really take you 3 months. But the fact was we built it in half a day, and we kind of proved the point that rapid prototyping gets people to those, to those outcomes. And we also got 250,000 video hits in a week, which was surprising for a talking fish. But the approach, okay, so what's Embed really focusing on? So in this room, we're all at Design West because we're embedded engineers and we understand how the electronics industry works. So it's worth taking a moment just to work out what Embed is and what Embed isn't. So we're really focusing on the tools for the very early stages of a product design cycle. So just when you've got some ideas, you want to code something up, you want to see if an idea is valid, if it works. Now, if it isn't, it doesn't matter. You haven't invested that much time or effort or dollars in it, you can toss it in the bin, and that's fine. If it is a good idea, then you've got a working prototype that you can take to your boss and say, well, now we should look at funding this properly and developing it properly. So it's really about those early getting started, experimenting with design stages. So once you've got your proof of concept on your desk, you can go and actually write your specification. And once you've written your specification, you can go start doing proper sort of product design. You're in the implementation phase that we all know and love so much. And the Embed sort of platform approach is really trying to build something that you can have your products built on top of. So we have the new concept of an HDK or hardware developer kit, and this is really a recipe of how you can pull together new designs based on these microcontrollers. It's not anything particularly smart or particularly groundbreaking, but the point is it leverages this whole investment that's going on in the Embed developer ecosystem for code reuse and hardware reuse. And the Embed SDK, one of the big developments we've had this year is that we've turned it into 2.0. Everyone likes their floating point versions these days, but 2.0 really means open source. So up until now, Embed has been a closed source platform where we've been experimenting with ideas, and we're now ready to sort of open it up to the world. Now this is significant for people developing products because an open source SDK now means that people can integrate it into their products and have confidence that they have full control over the source. And it's been released under Apache 2.0 license, which means it's very permissive. People can use it with confidence. So we're not trying to replace any of the existing tools that are out there or any of the existing development boards or evaluation kits. That's not what we're about. We're trying to get people experimenting with this technology, trying out new ideas, and once they do, hopefully more of them will lead to product developments. So just a few words about the SDK. So the C++ SDK is designed for sort of ARM Cortex-M microcontrollers. So we have a very high level sort of API providing a standard environment around that. And the idea is it's a very pragmatic implementation of certain blocks. So if you're experimenting and you need UARTs, well, the likelihood is you want to be able to set a baud rate and send and receive bytes. Every vendor has their own little special things that make their UART better than the next person's UART, but to some level, actually, that doesn't really matter, certainly if you're prototyping. So we're trying to take a very sort of pragmatic view of what these things should behave like, and it's very sort of behavioural level sort of interface. But you can dive down all the way to the hardware if you want. It's been developed on top of CMSIS, so it's CMSIS compliant. So it is still conforming to all the sort of industry standards that we know and love so much. And it's also, or the Embed environment allows you to export to offline tools. So once you've done your online hack-up experimentations, there's no reason why you can't then take that project and import it into MDK or IAR or CodeRed or just a GCC toolchain. So it really gives you that forward path. And as I said before, it's all open source, so it's under a very permissive 2.0 Apache license, so you really can take it, adopt it and run with it without worrying about the lawyers. So a few words about the HDK. Everyone seems to nod and understand what an HDK is these days. It's an acronym we made up in January, just before Embedded World, because we had no name for it. But it has started to really resonate with people. They kind of understand what it means. So it's an MCU subsystem with a debug interface. So for an MCU, you need a mechanism to get the image into the flash. You need a way to be able to debug it. So why not, as the Embed team tends to do, we'll hopefully do a very good job of it once, make it publicly available, and then everyone can sort of reuse that. So it's a two-chip design. The interface chip gives you all the usual things that you're going to need on a development board. So it gives you your USB serial port. It also gives you your flash drag and drop program interface. It also gives you a CMSIS DAP endpoint, which means if you're developing a product or an evaluation kit around the HDK, you can then target to that from any offline toolchain. And as we said before, it's all built on top of industry standards. So it's a USB device. We have CMSIS DAP for your debug. So, and also it works with Windows and Linux and Macs, because it is just USB based applications. And as with the SDK, it's free for commercial and non-commercial use. So we're making this stuff publicly available because we really want people to adopt it and just run with it. So just to clarify what we actually mean by HDK, as I say, it's kind of a new concept to us. Essentially, we have a Cortex-M MCU behaving as the embed interface. We have the target. So in the case of the embed that we're going to be using today, it's an LPC 1768. Your development board is of course a superset of that, and it has the things on it that makes it a development board, but this is really the core MCU subsystem. And over your USB, you get your programmer, you get your debugger, and you get your comms port. And again, it's just hopefully just solving the problem once and for all, so that nobody else has to visit it again. So in terms of embed-enabled hardware, so these are the NXP boards that are currently available. We led with the 1768 embed back in 2009, and that's been tremendously successful, far more so than I think any of us ever predicted. It's been slashed right the way down to $49, which, depending on who you are, you think is either a bargain or a rip-off. I'm not going to open that question here now. We get a certain amount of heat from the hobbyist community who think $49 is expensive, but they only seem to see it as $49 for a piece of hardware. They don't seem to place any value on all of the work that's done on the back end of it. But at the same time, you go speak to a company who are basing their product designs on this. Some of them actually even building the module into their products, and they think $49 is a bargain, so we shall see. So all of the boards are sort of HDK compliant, so you can take the reference designs of these boards and go integrate them into products. So if you build a prototype around one of these boards, you've then got a route forward into production. So the one in the middle is the Cortex M01 that we released last year. So being an M0, it's sort of lower power, a bit lower speed, or no, it's substantially lower power, a little bit lower speed, but it gives you that sort of price performance point. It's a USB device, so you can imagine it going into all those sort of applications that need the capability of USB, but also the low power and low costness of Cortex M0. And although it's not actually available today, it's going to be available very, very shortly, is the Cortex M0 Plus platform from NXP. This is the LPC 800 Max. So it's an M0 Plus in an Arduino form factor that leverages the whole Shield community from the Arduino guys. And I think there is a registration program about to start to get samples of this, so keep your eyes out for that. That's just repeating more of what I've just said, gives you an idea of the capability. The reason I think the M3 one has been so successful is because it is such a high-end part. An M3 at 100 megahertz gives you certainly a processing punch. It's got half meg of flash and 64K of SRAM, which for people used to being constrained, that's quite liberating. But it's also got USB host and device and Ethernet and CAN on board. So that's a substantial amount of sort of punch to be packing for such a small board. Now the 800 Max board that's just coming out, it's as I say, it's based on the LPC 812 part. That's I think the part itself is available and the board's following up. And what NXP have done here is leveraged all the different platforms that are available to them. So Max apparently stands for Mbed, Arduino, and Espresso. So it really is taking the best of all worlds. So if you think LPC Espresso, you're familiar with the IDE from the Code Red guys. The boards have their LPC link on board, so you don't need an external sort of debug probe. So there's this whole LPC Espresso world that is very well established. They've got lots of users, lots of sort of development going on around it. So yeah, that's great stuff. But the LPC Max board is also Mbed enabled. So if you get one of these boards, it's going to be another very low cost sort of $20 development board. You plug it in, you get going, you're on the Mbed platform, you have the online compiler capability, you have all of the sort of online developer community that we've built up around the Mbed platform. And it has things like the CMSys DAP compliant things. So if you build a prototype with this and want to do some offline debug, well, you can use any of the industry standard tools. But I personally think the best thing about it is it leverages all of the effort that has gone on for the Mbed platform. So over the last 5 years, people have been developing libraries for accelerometers and LCDs and all manner of things. And because it's all built on top of the same standard API, anything that's been developed in the last 5 years is just as appropriate for this new board that we've done as for any board. So I think that level of code reuse is really what's building momentum around the Mbed platform. So there's a nice little picture of the board. You can see it's Arduino style sort of headers. There's the Mbed / LPC Espresso footprint, and it really is a minimal board. We have the the interface here. This is the actual target part itself. This is the M0 Plus. You start to realise a sense of scale when you see how big the crystal is compared to both of these parts. But one thing that the NXP guys have done, and I think this is particularly neat, is we can actually rip that crystal clean off the board, and it runs anyway. And it also runs with USB full speed running. They've done some I'm not sure whether it's public if you get to see the implementation because it's public, then you'll look at it and smile because it is beautifully elegant. Yeah, I'd like to see if there's an app note published on that. But yeah, you can rip that crystal straight off. It's another component off of your BOM. You've just saved another whole bunch of board space. It's a beautiful thing. Right, so that's the 800 board. Now the message that we're really pushing around this is about what you're getting into when you get an embed. What's the promise that embed is making. So we've said that we've got this whole SDK that people are building upon. It's very portable. Lots of development, and it's sort of can be used for commercial applications. We've got this HDK which we're hoping to really bootstrap people's project designs. Now the free online tools we think are still very, very, very valuable if you're just doing quick experimentation. It really gives you a toolkit to get started with. And the development community is pretty substantial worldwide, very active. Because we got a lot of heat from this in the early days, we kept the forums and everything shut unless you owned a board. So the only way to have an embed count was to own an embed. And although it was a bit controversial, I stand by that decision because if you look in our forums, there's no flame wars going on. Everyone on there isn't just spouting opinion, they're spouting fact on the basis that they own one of these things. And we're hoping that, we've set the precedent now. And as the community grows, I think people are following suit. So I think it's a really helpful community of developers that are actually getting their job done using the platform rather than going there for flame wars and as a hobby. So that's the embed platform. And now, possibly foolishly, I thought it'd be really good to do some live coding demo examples. What could go wrong with that, right? So we do have slides for all this. I'm going to be switching between slides and doing stuff. Certainly in the online compiler. So for those of you not familiar, that's the embed micro. It's in a little dip form factor, which is great. You can solder to it, you can stick it in a piece of breadboard, you can play. We've recently pushed this out there, which is the embed application board. Sort of credit card size, there's a whole bunch of stuff on it. You'll probably see later, little LCD and accelerometers and stuff. But more importantly, it's got all the stuff on there that's hard to solder and you can't put it on a breadboard. Ethernet sockets and USB sockets generally aren't breadboard or stripboard friendly. Anyway, we'll plug our embed microcontroller in, which is where it gets its power, and hopefully it'll also pop up and enumerate as a USB flash disk. Now it really is actually genuinely just a flash disk. There's a little bit of flash memory on it that uses to implement a file system, and that is actually significant. We'll see a little experiment on that later. So we follow the permanent embed.htm file that's on there, and it is linked straight through to the website, and it gives us the ability to sign up and create an account right there. Sign up is now actually open on the embed.org website, but you need a piece of physical hardware to get the compiler license. So you can play around with the compiler, but if you want to compile for a specific target, you need the license. I mean, the licenses are free, but just you need a piece of hardware to prove that you have one. You'll not be surprised to know that I actually already have an account, so I shall log into that rather than creating a new one. Okay, so the embed website, when you first visit it, hopefully there's some useful resources sort of on the front page. You can see what's going on in the blog, sort of questions and answers, sort of Stack Overflow style. So there's lots of people sort of helping each other and sort of solving the problems. We have the handbook. Now this is the official sort of embed maintained reference manual, as it were. So it gives you all the information about the SDK, the HDK, the compiler, getting started guides, and then all the documentation on the certain the parts of the sort of API library. The API library includes things like we've done a TCP/IP port. There's an implementation of CMSIS RTOS, so there's RTOS support in there as well. We've done a USB device and USB host library. And the reason we're taking this approach is, we're trying to identify the things that are actually quite hard to do and do it once and do it properly and make it freely available. I make quite a lot of use of the USB host library. I certainly couldn't code one from scratch. Life's too short, and that's what we're trying to solve. So that's the the handbook. There's a cookbook, which is kind of like the community area. So this is where people who have done libraries or example programs or projects, this is where they get to publish some of their code, share it with the rest of the community. There's lots about the TCP/IP networking, the HTTP clients, SMTP clients. There's lots of stuff going on in the Internet of Things, as you can imagine these days. USB, LCDs, audio, wireless, RFID. So there's quite a lot of stuff here that's already been published, and that was my point earlier about the LPC 800 board. When it comes out, it's just going to instantly be backwards compatible with all this stuff, and we think that's the power of the platform, is that it gets to leverage everything going forward. So as you can see, there's actually quite a lot of stuff out there now. But the interesting thing is the online compiler, because this really gives us the tools to very quickly get started and experiment with some ideas. So I'm just going to fire up the compiler. As you see, it's just running in the browser, so it doesn't matter whether I've got a Mac machine or a Linux machine or Windows. All you need is a browser, basically. I'm going to create myself a new project. Now, every time you create a project, you get by default something that's going to compile and build and do something relatively interesting. And in this case, no prizes for guessing what that's going to do. We can compile that. As I said earlier, this is just a USB flash drive. I've compiled my code correctly, so it gives me a binary to download. I download it straight onto the board, and you'll see the little light flashing as it downloads. And now it's on there, I can press the button and we're good to go. LED 1 is flashing. So you've probably all been through the pain of a new development board where it takes you the first half a day to get an LED flashing, then you're off and running, and it incentivizes you to carry on. So if I just branch back to the slides for a second. So let's think about sort of other things you might wish to do. So if we go back to the online compiler, we'll notice that by the embed library is a list of all the sort of high-level API calls that are actually available on this, and hopefully they're nicely documented in a sort of logical sense, and you can see what they do. So for instance, here's the analog in, gives you an example of how to go read an analog input. So the second example is literally just going to pull on that and see what we can do with an analog input. So rather than just flashing the LED, which we've done so far, how about we plug this board now into the embed application board. And we're going to use these little potentiometers to influence our design in some way. Now again, not that it's particularly difficult, but if I was just doing a regular development board bring up, I've now got to go get the reference manual out and work out which registers I've got to poke to power up the A to Ds, and make all your shifting too many bits left, all those sort of annoying problems that we've done, and what embed really sets out to do. Call it laziness or call it sensibleness. Here's one I made earlier. So all I've really done is included an analog in object. So basically all the analog in objects are nicely mapped out onto the board, so we can just include an instance of the object, we can give it a name and tell it how we're going to connect it to the board. And in our while loop now, rather than just waiting for a set amount of time, we're going to make a very quick call to the A to D converters and use that in our calculation. So hopefully if I now compile that, save it down onto my application board and press the button. So I now have an LED that I can flash faster or slower by a part. I mean, it's not particularly awesome, but the fact that you can do it very quickly is sort of relatively interesting. So that is using other bits of hardware to influence a basic circuit, but let's go and think about other things that you might wish to do. So usually, if you're going to start bringing up more and more complicated things, you're going to need some way of seeing what's going on, or at least have some initial debug. Now, debug, not in a sort of debug probe sense, usually means LEDs. It usually means printf or an LCD of some description. So the embed environment has an LCD driver. It's one of the first things we wrote back in 2000 something. They're all pretty much standard. We've published a library for it. But more importantly, we've published a cookbook page which kind of encapsulates what it's all about. So this is a text LCD, here's the library, here's the getting started sort of Hello World program, which is pretty foolproof. Now they're all pretty much standard in terms of how they're pinned out, so this is how you wire one up to your embed and know that it'll always work. And the reason this is significant is you want people to do something, follow instructions, and it work for them, because if you can do that, they'll do the next step. So if I go back to my online compiler, again I've already imported this to save time. I have a nice example here of of the text LCD or the LCD. It's actually a graphics LCD, but it has sort of text capability. So the nice thing is we're trying to abstract everything to the highest possible level. So if you're talking to an LCD, things like printf are the obvious way forward. So the LCD library that's been written for this, not by us I may add, by one of our community users, has given us a very sort of high level, clear screen, locate, printf command. You know, everyone knows how to drive those sorts of commands. So again, if I compile that, bring it down onto my board. So we thought we had a unique opportunity to actually start providing people with mechanisms where they can pass projects around in their entirety, and we can do that because we're online. A project is just a URL. So, for instance, if I'm just going to delete the LCD library out of this project. So now, if I go to the Embed application board, this is just the web page we wrote about it. It shows you all the features. The first thing is the LCD. It's a reasonably interesting thing. If I want to import this project wholesale, because I've got one of these boards, and the first thing I want to do is make sure it works nicely, well then all I need to do is hit this link here, import the program. So that takes you, because it's URL, it fires up your browser, which is just another URL. You tell it you want that to be called, so new LCD. So I've now just imported that project that someone's written and published on it for their own motivation, and that's being pulled straight into my compiler account. Now, although it doesn't make any guarantees about how good other people are at coding, but it does mean if their program worked for them, by sharing it with me by URL, then I can recreate exactly what they recreated. And we think that's significant also. If you look at what happened in the early 80s of the way computers developed, a lot of it was about critical mass and commonality and the ability for people to share. So I might have just been Skyped or emailed a URL, I've pulled it straight into my online compiler, and I know that I can hit compile on that and it just work. And we think that's particularly powerful. But similarly, if I don't want this sort of dumb application, I just want to use the library, well that's fine also. I can take the library that's been written for it, which we have a high level of confidence in because it's officially published, and I can hit the import this and bring it straight into my program without having to worry about all the usual issues around importing people's code. So that's the text LCD, or the graphics LCD. So now we have a way to actually print something to the screen. It's interesting to think about what other things, firstly, are on the board, because we have it in front of us, but also the sort of things people want to do. Now if we take the world of sensors, we've already said earlier on that the thing that distinguishes a microcontroller is the fact that it interacts with the real world. And that means sensing, it means interfacing with stuff, it means actuation. So this board happens to have a temperature sensor on it, because people like to monitor the temperature of things. It's very simple. There's a little I2C device. It's soldered down onto the board there. It's only 4 pins, power, ground, and the 2 lines you need for I2C. An interesting thing here is we've taken, again, a very pragmatic approach towards I2C. So if you're trying to do an I2C, if you're trying to talk to an I2C device, at some point you don't really care about the I2C state machine or how horrible it is or the register map that you have to go and poke to make this thing happen. You're really just interested in exchanging bytes with the device. And at a prototyping level, that's all people really want to do. So if we look at the I2C interface, it gives you an idea of sort of the level that we've abstracted to. Keeping it simple is always the watchword. There's the ability to set the frequency of the bus, write bytes, read bytes, write packets, read packets. It's a very sort of high level way of doing things. So if we go back to our online compiler, it just so happens that I have an example program here that does something very, very simple. It takes a temperature reading and spits it out both on the LCD. Now the other place it's going to spit it out is onto this other serial object that I've called PC, which actually communicates over USB, TX and RX. Now, you remember I plugged this thing into USB, so one of the other things that we've made available over USB is a USB serial port, because they're always pretty useful. So if I compile this program now down onto my board and hit reset, I can bring out something like TerraTerm or any other user application. I'm now reading temperature and spit it out over the USB serial port. Again, it's not particularly groundbreaking. USB serial's been around for a while now, but it's just another one of those things that you can give to people for free, and it just makes their life a little bit easier. Now I'm going to pick up the pace a little bit because I know time is running out, and I think you want to see some interesting stuff, not serial ports. So let's think about data logging. Now, everyone has their own pet data logging example. We've already seen how very easily I can rip temperature readings out of my sensor and print it over USB to the screen. That's pretty useful stuff. Now, you've watched every time as I've downloaded things onto the USB flash drive that it gives you the programming interface for Mbed. Now, one of the things that we've also done is we've made that bit of storage available as a semi-hosted file system. So I can open a file handle onto the Mbed drive and read and write from it just like I could do from any other sort of standard system. So it's very standard C stuff, fopen, fclose, fprintf. And again, it's not particularly staggering stuff, but again, it's one of those productivity things that really gets people sort of off and running. So if we go back to our online compiler, I have an example here. It's exactly the same as I've just run. Actually, no, I'm going to wiggle the pot on this one rather than do temperature because that's more fun. So I have my pot, and I have an LED which I've created just so I know when I'm done. And I've got this new object called local file system, and I literally just take a file pointer onto that file system. I run around a loop 100 times, taking a sample and spitting it out to the file, and then I'm going to close. Now, because a fat file system can't have two masters, whenever you open the local file system from the target device, it vanishes momentarily from the computer. So my Mbed drive will actually vanish for a bit, and that's okay. You can see it flashing there as it's taking samples, so I give it a wiggle while it's taking samples, and now it's done. And now my Mbed drive should reappear. Unfortunately, Windows is a little bit lazy with refreshing drives, but when it comes back I should have this data.csv file on my drive ready to go. And the reason I've called it data.csv is because now I can open that straight up into something like Excel. Okay, maybe I didn't record any values. Okay, we'll give that another go. So it is pretty neat. It'd be neater if it worked a bit more slickly in front of a live audience. But, Right, now, so if I open this one, I get all my samples there. And then I can just do, insert a line graph. Okay, I didn't actually wiggle the pot that time. Those one is there. Okay, but now you could have seen what could have happened, right? So I could have gone from just trying to do a quick experiment to now actually I can start taking values and doing something sensible with them. So that's vaguely interesting. But then what about? We've only got a 2 megabyte drive here. The Mbed drive is only 2 megs because that's about the size you need for a bunch of binaries and some configuration file. We're not really in the business of trying to be the world's flash disk. But obviously some applications do need to run for a substantial amount of time. So let's think about other capabilities that people want. Now if you think about mass storage, everyone is sort of more than familiar with these things. They're everywhere, you recognise them. You've generally got a whole bunch of stuff in, or a bunch of them in your desk drawer. So let's think about how you talk to one of these. Now, it's not actually trivial. Fortunately, we have software people who make this stuff work for us. As a hardware guy, I can understand I can solder down a socket. That's not the problem. It's the amount of stuff it needs. So let's try whacking this thing in here. The hardware's done. Brilliant. From a software point of view, you need an RTOS to run this stuff. You need a USB host stack written. Obviously, that's got to sit on top of the file system. So it's not a trivial challenge. But again, we try to be pragmatic, solve it once, and then make it available to people. So we go back to the online compiler. I've already imported the version of the mass storage file system. So it's basically exactly the same as the local file system. You'll notice actually the application code itself hasn't changed. All I've done is made an include of USB storage file system and made an object for it, and all the rest of it is basically transparent. So hopefully if I compile that down onto my board, again I'm sort of glibly using this stuff without really appreciating how complicated the underlying software is, but so hopefully that's going to be running now. It's going to be taking some samples. See the little flash disk flashing as it writes them. When it closes the file handle, it's going to flash as it's storing. Rip that straight out. And hopefully I'm going to have a CSV file with something useful in it this time. There it is. And I go exactly through the same process again of saying, well, let's insert that into some kind of line graph, and that was me wiggling the pot. Now, this instantly takes a few hundred kilobytes of flash and some kilobytes of SRAM into something that can actually now have gigabytes and gigabytes of storage. So yeah, it's quite a powerful thing. And even though obviously it's tremendously canned because it's for a live demo, you can understand how easy it is to take that. I mean, although I did spend an hour putting this together in an hour is still substantially more simple than it may otherwise be. So that's the stuff that's relatively fun. If you go back to the presentation, hopefully now you've seen how easy it is to do things like leverage the file system. Another thing I will say, even though I don't do any examples in this sort of Hello World session, the approach we've taken here is that the mass storage file system has exactly the same API as the local file system. So your application code doesn't really care about the implementation if it's doing file access. So if I want to start off experiment with some application, I'll use the local file system, and when I can be bothered to wire on a USB connector, it's two code changes, or 2 lines of code to change, and you've just retargeted the whole thing. Now we've done exactly the same approach with the networking, so we've got a very all of our networking things are abstracted to essentially a C sockets library, and then we build things on top of that. So for the Ethernet interface that is on board on this device, you notice that there's an Ethernet jack on there. All of the the HTTP clients, the WebSocket clients, and all the things we've built on top of that are built onto the same API. So I can use quite happily for experimenting on my desk an Ethernet connection, and then when I decide I want Wi-Fi, well, it's in exactly the same way. It's just 2 or 3 lines of code changing, and now I'm talking over Wi-Fi. If I want to use mobile broadband dongles, again, it's a couple of lines of couple of code changes, and we're off to go. Now, the thing that also was big in Embed 2.0 was the whole idea of CMSys DApp. I don't know, quick show of hands, anyone familiar with CMSys DApp? Okay, a little bit. So CMSys has obviously tried to defragment how you abstract a processor core. We've tried to extend that to say, how do you abstract the DAP, which is the debug access port, which is how Cortex processors talk to flash and RAM and that sort of thing. So basically the DAP has its own command set, and we've repackaged them over USB, and we've published it as an open standard. And the idea is to help defragment the industry. ST have ST-Link, NXP have LPC-Link, Kyle has U-Link, there's J-Link, there's lots of links out there, and it's just ridiculous because everyone has to support, it's politics. So if we create a new standard that belongs to everyone, then everyone can adapt it and adopt it and support it without having to get too upset about their own solutions. So what we've done in the online compiler is given people the ability to, if I take a very, very simple example here, is export into an offline toolchain. So for this test program here, I can export, and it's 1768. I'm going to export it to Microvision for the obvious reasons. I'm going to whack it here on my desktop. So I now have all of the embed libraries, everything I need to recreate this program offline outside of the online compiler. So if I go back to my my desktop, I've got the zip file that I've just created, and I can extract that here eventually. And I've now got myself a file that contains everything I need to recreate that project. And I've also got the file here that launches the MDK tool. And we've done exactly the same with IAR and CodeRed and GCC. So once you've exported it, you are literally into the world of this toolchain. So apart from clicking that UV UV, whatever it is, project file, I'm now in the embed MDK tool. Now the thing that we've provided, the third thing we've provided over this USB cable now is a USB implementation of CMSys DAP, which now means that IAR and all those other tools, MDK, Code Red, can actually target this thing natively over USB. So the drag and drop interface isn't used at this point, but we still have those capabilities. So I can now compile my program, and once it's compiled, I can just inject it straight into the board, as you would do if you had a regular ice box and it's going down there. So hopefully now my LED is flashing because that's what the application was. But I'm now into the world of debug. So this is the first time that you've been able to do this kind of debug with the embed hardware. So I can set my, breakpoints on there, and hopefully just be able to go through them one at a time and see what it does. So I've gone from let's hack up some little experimental program in the online tools. It's all very quick, it's all very experimental, but now I'm in the realms of, well, I've got a proper tool here and I'm doing proper debug. So I've gone from hacking around amateur to this is actually what professional developers do, and I could have done that in hours rather than having to worry about big project development cycles. So just by way of a quick summary, so we think there's a massive opportunity for microcontrollers going forward. Costs are coming down, capabilities going up, and we're hoping that Embed 2.0 is really going to become a platform that people can build upon, so they don't have to worry about all the ugliness below. So fast turnaround of experiments, and then you can build upon the SDK and the HDK as really as a way to bootstrap your product development. And then, of course, really leveraging the developer ecosystem that's appearing on top of that. So the fact that we work with Sprint in the US and Vodafone in Europe for providing 3G data dongles, and it's all those kind of ecosystem partners that are really bringing value to the platform. And of course, it's very accessible. I mean, you've seen how we could have done a very, very quick development demo there. I chose not to code it live, but you can really go from just hacking around to doing USB data logging in sort of hours. And again, that really comes down to the desire to get people up and running really quickly. So Embed is really sort of focused on trying to get people prototyping and experiment, and with very, very broad appeal. Now, it might be engineers that are new to the industry completely. So they've got the smart people, but maybe they're a mechanical guy, but they understand electronics is good for them. It might be experienced users. I consider myself reasonably experienced, but I still turn to Embed because it's just a quick way to get things done. And we're even finding the marketing people, distributors, they love it because it's a great way to showcase things that are pretty simple.